So last time we talked about the fabrication of the transistor itself. So we have the source, drain, the channel here, and we have the gate. So next step is to make the wiring. Make the wiring to the terminals. So first, we need to remove this oxide. So we have an oxide here. We need to remove this oxide. Then we do the metal. We deposit the metal. So we first activate the oxide. We activate the oxide from this part. Activate the oxide, and also activate the oxide from here. Then we deposit titanium. So this titanium is typically 100 nanometer deep by 100 nanometer thick by spatter deposition. Next, we do an annealing process. We do annealing in the nitrogen environment. So there are two purposes for this. So first, for the annealing, so when we have the titanium on top of the silicon, it will form at the interface, it will form a titanium silicide. So this is to form the TiSi2, titanium silicide. So what's the purpose for this? So we know that for the metal semiconductor, contact. So we have something called the Schottky contact. We have something called the Schottky contact. So you can look at, let me see. There is the metal semiconductor junction. So when we put the metal on the semiconductor, there may be something. It's called Schottky contact. So we may have this thing called the Schottky barrier. So that means there will be very high resistance. If you draw the energy boundary diagram, it's something like this. So it can be something like this. So we have. So on the left side, so we have the metal. For the metal, so we have the Fermi level. So on the right side, so we have the silicon. So for the silicon, so we have this energy band, conduction band, valence band. So this is the contact. So you can see if we have electron here, electron come to the right side, needs to come from here to the right side. So we need to overcome the energy barrier here. So this barrier is called the Schottky barrier. So when we have this energy barrier here, we have very high contact resistance. We may have very high contact resistance. To remove this contact resistance, so we can have this titanium silicide alloy. So that means, so we have here titanium here, silicon here. So in the middle, so we have this titanium silicide. So here we have the gradual transition from the metal to the silicon. So we do not have this barrier here, energy barrier here. This way we get smaller resistance. So on the top part, so we have this titanium nitride. So this one is also conductive because we have the nitrogen. We form the titanium nitride. So next, we will pattern the metal layer here. So we do spinel resist, photolithography. We activate the titanium nitride. So in this case, it's activated by this white etching, ammonium hydroxide, hydrogen peroxide, and water 115. So this is also called RCA cleaning. So we will learn about RCA cleaning later on. So this you activate the titanium nitride. They will leave behind the titanium. So here is titanium silicide. So here we have titanium. If you remember titanium TiSiO2. Then we do an annealing process. We do another annealing process to reduce the resistivity of titanium nitride and titanium silicide. So next, we coat the layer of the silicon dioxide as a insulating material. So this is done by the low pressure chemical vapor deposition. If you remember, we have shown two ways to deposit the silicon dioxide. So one is using the silane gas plus oxygen to form the. Another choice is the silane gas, the dichlorosilane plus N2O. N2O is also from the silicon dioxide. We form a layer of silicon dioxide. So very often we add some phosphorus. To the feeding gas. Then it becomes a PSG, phosphorosilicate glass. phosphorus silicate glass. So that means the material will be silicon X, Y, Z, something like that. As silicon, phosphorus, oxygen, X, Y, Z. So this is the material. So the purpose for the phosphorus is to block nitrogen ion, so sodium ion. So we know that the sodium ion is very bad for the device because it move around easily within silicon. So we should get rid of the sodium ion. In fact, even for the many clean room, they do not allow sodium hydroxide or maybe sodium chloride. The many clean room, they do not allow sodium in the clean room. So by doping the silicon oxide with phosphorus, we can block it. We can block this sodium ion. Another dopant may be the boron. This is called BPHG, boron phosphosilicate glass. It will be something like this. So silicate, boron, phosphorus. Oh, you can see X, Y, Z. Another number. Say 2. Okay, another number here. So when we put the boron in the glass, it reduces the flowing temperature. That means if we do a high temperature process, because of the flowing, it may smooth out the surface. It's good for the polymerization of the surface. But in this case, we will make the surface flat by the chemical-mechanical polishing. So the next step is the chemical-mechanical polishing process. So why it is called chemical-mechanical polishing? For chemical, we add some slurry. For instance, we add QH. So we can make the slurry base, the pH, high pH. Then there will be some chemical reaction. So we have the chemical component. So mechanical, so polishing itself is mechanical. So the idea for this is that, so when we have both mechanical and chemical, then the polishing rate is much higher than mechanical or chemical alone. That means they usually come to each other, they help each other to have the polishing rate much faster than pure chemical polishing or pure mechanical polishing. So then we have the flat surface. So next, we need to etch holes. To open the contact. So we simply resist photolithography, etch away the silicon oxide, etch away the silicon oxide to produce the holes. So silicon oxide is etched by the plasma etching. We remember, so we can use this gas to etch silicon oxide, as we talked about previously. Then we need the metal. We need to fill in the metal here. We need to fill the metal into the hole. So this is called the stud. It's called the stud. It's also called via. It is actually just a pillar. So we make a metal pillar into the holes. So what do we do? So first, we coat a thin layer titanium nitride barrier layer. So this barrier layer isolates the tungsten from the glass or from the silicon. This is the connecting barrier layer. Then we do tungsten CVD, chemical vapor deposition. So we use WF6 gas and hydrogen to form tungsten metal, and this is gas is pumped away. So this way we have the hole filled with the stud, with the via or with the pillar. Then we do the polishing process to remove the metal here. So we do the polishing to remove the metal on the top. So next, we need to pattern another metal layer on the top. So this is done by the aluminum. We deposit the aluminum layer. We do photolithography. Then we etch away the aluminum. So we have the aluminum. So this is the wiring. It's also called interconnection. It's also called interconnection. So the aluminum is etched away by plasma etching. We can use BC, the mixture of the trichloride boron and chlorine gas to etch away the aluminum. The etching product is aluminum trichloride. So this one is volatile. So then we etch away the aluminum. So usually the aluminum is not pure aluminum. We add a little bit of silicon So we have small percentage of silicon and copper into the aluminum. For the first part of silicon, so if we have the aluminum, on top of silicon, then at high temperature process, the silicon can get into the aluminum. This way, so aluminum will corrode the silicon from the device region. So this is not good. But if we have already silicon, silicon in the film, then silicon here will no longer come to the film. So that means we add the silicon to avoid the erosion taking away the silicon from the device layer. So we add the copper is to reduce electromigration. So if we have an aluminum film, you apply some voltage. What will happen is that the aluminum atom will move around. The aluminum atom will move around. So this is called electromigration. So the atom will move around when you have the electrical field. When you have move around, leave behind void. This is not good. So by doping it with some copper. So when we have the copper in the aluminum, this aluminum will be kind of fixed. It will not move around. So next step, here we have the first metal layer. So we do the same thing for the second metal layer. So here we have the silicon oxide. Then this is usually it's also silicon oxide. So this is also a silicon oxide. Then we do the this is called the slat. So we do the slat again. We do the aluminum again to repeat the process. So finally, we coat a layer of silicon nitrate. So this is called a passivation layer. So this layer is very dense. So like a water, like a sodium. So those things, they will not go through this silicon nitrate. It's very dense. It is more resistant and denser than silicon oxide. So then this is the final device. So in the end, we do a annealing process. It's called the forming gas. So 10% hydrogen in nitrogen to reduce the metal, to allow the metal contact and reduce the electrical charge at the silicon dioxide interface. So up to now, we have finished the fabrication of the device. So here the silicon nitride is not covered everywhere. So somewhere outside, the metal has to be exposed. So we can do the wire bonding. But here in the drawing, it looks like the metal comes to here and comes to here. Actually, obviously, the metal will not go through the films. It is those wire bonding is on outer side or other places of the device. So then it's done. So here's the layout. So this is what you see. This is the cross section. So this is the cross section view of the device. So now we want to look at the top view. So what does the top view will look like? So here is the top view. Top view of the inverter. This is the inverter. So if you remember, input 1, output is 0. Input 0, output is 1. So this is the inverter. So here's the layout. Here's the layout of the inverter. So we have the PMOS here, N-well, source drain. We have NMOS here, source drain. We have the metal contact. So this is output. We have this electrode and this terminal here. So we start with the here N-type silicon, but in this slide we usually start with the P-type silicon. But there is some, if you are careful, you see there is some small mistake. For example, if we look at here, so the output, so the PMOS, this is the PMOS, right? This is the PMOS. So PMOS is connected to the high voltage. So but if you look at here, this is the PMOS is connected to the low voltage. So this one should be high voltage. So this one should be low voltage, or maybe ground, or you can say the ground or low voltage or negative voltage. So it should be the opposite. So this is the layout of the device for the inverter. For other like NOR, NAND, so other logic circuit is more complicated layout, but the basic idea is the same. So this is the technology. This is the technology in the 1990s. So afterwards, there are new development. The first one is the nickel-silicate. So in the slide we talk about titanium silicate, but later titanium is replaced with nickel. And later on, Intel they want to replace nickel with the cobalt, but this one is not so successful. So that's one major reason that Intel now is lag behind. Intel is lag behind TSMC. Taiwan Semiconductor Manufacturing Corporation. So Taiwan Semiconductor Manufacturing Corporation. So now the stock value for the TSMC is higher than the stock value for Intel because Intel does not make the cobalt work well. So the gate oxide is only 1.2 nanometer gate oxide, but actually nowadays we no longer use SiO2, so we have this thing. Maybe remember this is the high K metal gate, high K metal gate. So we no longer use silicon oxide, we use high K material like HF. As we talk about in the slide, it's high K material. Another trend is the strain silicon. How to strain the silicon? If we have if we dope some silicon germanium into the silicon, you can imagine so the lattice constant of silicon germanium will be higher than that of the silicon, right? Because germanium atom is bigger than silicon, so the lattice constant of the silicon germanium will be higher than the lattice constant of the silicon. So if we coat silicon germanium on top of silicon, the lattice, if this is atoms, they will be stressed. There will be some, it's called strained. So the lattice constant will become bigger. So this is called strained silicon. So when you have the strained silicon, you get faster carrier. That means you have the higher mobility for the electrons and for the holes. We have the strained silicon. So this is another improvement, higher mobility, because the silicon is stretched, the atom is stretched by the epitaxial layer silicon germanium. Another major trend is the low K dielectric. So here, if we look at the material here, in the 1990s, as we talk about in the slide, it is SiO2. So this material is not very good because of the RC delay. RC delay is big. So what is RC delay? So imagine, so you have the, I draw it here. So you have here the metal here. This is like two terminals, like this gate, and this is the source of another device. So you have the metal wire. If we apply voltage here, if we apply the voltage between here and here is not the same as the voltage here. It takes some time. It takes some time for the voltage between those two spots to reach the value of the V. But this is the delay. So time constant is called RC. The time constant is RC. That means it takes about RC times for the voltage between those two spots to become the same as these two spots. If we look at the circuit, we can draw something equivalent circuit. We can draw something like this. So we have this capacitance. This is the parasitic capacitance. If we look at wire, so metal here, there will be some capacitance between those two metal wires. So then we have the resistance. So the metal, we have the resistance. Then so we have the switch. Then we have the voltage. So here we have the voltage. This is the switch. This is the resistance. If we switch this on, so we want to know how fast the capacitance will be charged with Q. So we can do the equation. So the voltage drop along this one is called IR, plus the voltage drop along the capacitance is given by Q over C equal to V, equal to the applied voltage, right? So I is R. We know the current is the change of the charge equal to V. So we need to solve this problem. So you can think then it becomes like R dq V minus Q over C equal to dt, right? So R dq divided by V minus Q over C equal to dt. So this one can be solved. So in the end, you get something like this. In the end, you get the equation will be Q over Cv. So Cv is the maximum. This is the Q0 equal to 1 minus E minus T over RC. Q over Cv equal to 1 minus E minus T over RC. So you can see the RC. So RC, this is the time constant. RC, that's why it's called RC delay. It's kind of time constant for the charging. So to reduce the RC delay, so first we reduce the resistance. And this can be done by using metal that is more conducting. For example, copper. So copper is more conductive. Conductivity for the copper is higher than aluminum. Another thing we should do is to reduce the capacitance. Reduce the capacitance. So how to reduce the capacitance? So we know that C equal to, so there's the capacitance. So here, epsilon R, we can use it for K. So C equal to K. This is another note. So people also use the replace epsilon R as K. Not S D. The distance. This is the distance. The distance between the two metal wire. You can think this is the D. The distance between them is D. So you can see when we have the low K, when this one is smaller, we get smaller capacitance, so we get smaller delay time. So what's the minimum for K? So K is higher than 1. So when K equal to 1, it means air or vacuum. So when we have the vacuum or air, K equal to 1. So otherwise, K is higher than 1. So for the case of silicon dioxide, K equal to 3.9 for silicon dioxide. But this is not very good. So how to make the low K material? So low K material is made of the porous. It's the porous material. So when you have the porous material, it is like the air. Then the K is closer to 1. Nowadays, the material here is the porous material. Here is kind of porous material. So next one is the interconnect. So in the lecture, we talk about aluminum. So nowadays, people no longer use aluminum because copper has smaller conductivity, smaller resistivity than aluminum. So this is done by this process. So first, so we have this. We call this a silicon oxide. Then we do the lithography and etch it. So we make the slat holes. They call the slat. It's also holes. Lithography and etch. Then we do another lithography and etch. Lithography is called wire lithography and etch to pattern the oxide. So finally, we do the metal deposition by electroplating. This is the electroplating process to coat the metal. Finally, we do the planarization. We do the chemical-mechanical polishing to smooth out. So this process is used for the today's manufacturing of the interconnections. You can see, so this is the cross-section of the CMOS interconnect. So on the below, so this part here is the transistor. So then we have this several layers of the metals. So those metal here is, so this is, if you remember, this one is copper. So this is copper. So the slat, those material here is also, everything is copper. Because you can see here, so the wire, so the slat and the wire, they are both copper by electroplating. So this cross section is produced by the focused ion beam. So focused ion beam to cut this cross section. We will talk about focused ion beam in next term. Okay, thank you.